Hello everyone, I'm Dr. Kim. This is help for homework 26, our last chapter. Chapter 26 is CC bond forming reactions in organic synthesis. The first, you should recognize what kind of coupling reactions are these, and then find the carbon which is going to make new bond, two carbons, and connect it, and then redraw the product. Draw the product formed in each reaction. That's 26.20. This is organocuprate, which is that's an alkyl group, and this carbon will have a new bond with this carbon and no stereochemistry change. So propyl group will be added to this cyclohexene ring. The alkyl halide or aryl halide, that carbon where the organometal, the carbon next to the organometal will have new bond. This is organocuprate, B, that's boron with palladium, 4 ligand. This is Suzuki reaction. So Suzuki, and the carbon with alkyl halide, carbon with boron. This will make new bond, and I'm going to redraw that. I'll draw this pyridine ring first. That's going to make new bond. And this carbon, new connection, will be meta to this methyl. So you have 6-membered ring and meta to this methyl. This is Suzuki reaction. C, there's alkene, double bonds. There's aryl halide, and this is palladium acetate with phosphine ligand. And then there's triethylamine base. Palladium with no other metal and double bond. This is Heck reaction. Heck reaction is going to make trans major product. There's a double bond, so I'm going to draw trans, and this carbon will be added there with trans fashion. So pyridine ring with alkene, then a trans, and this carbon is this carbon. There's furan ring, and that's trans. The next D is lithium with copper iodide. This is going to make organolithium compound, halogen metal exchange, and then that organolithium compound will be converted to organocuprate compound. This carbon and this carbon will make organocuprate coupling. So that's cis. I'm going to maintain that cis. Then this carbon is that carbon 1, 2, 3, 4, 5, 6, 7, 8. So this is octyl. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 1, 2, 3. So this is your product, and the cis remains. E, that's palladium with boron. This is Suzuki coupling. The carbon next to the boron and carbon next to the alkyl halide, the halogen, will make bond, and this remains cis. New bond is trans to this from this aryl borane. So that's trans. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So cis, trans. 2,4-hexadiene. F, that's the carbon with halogen, and that's double bond. Again, that's a Heck reaction. It will make trans product. Oh, that's our old exam question with electron withdrawing group. We'll make trans, and there's benzene ring, and this methoxy is para to this carbon, so there's methoxy, OMe. G, this is how to make a boron compound. Anyway, boron compound, the carbon of the right carbon is this carbon, palladium boron. This carbon, this is a vinyl halide, that's gonna be connected trans fashion. So you have that and trans to the benzene ring. UCC1 forms. This is trans. This is again Suzuki. Suzuki is palladium with boron. Here, hydroboration occurs with triple bond, and boron will be added to the least hindered site. So I'm going to rewrite H. Then there is tertiary butyl group. There is another H. This is boron with cyclic structure, boronic acid. And here you have bromobenzene. The carbon here and carbon here will make bond. You have triple tertiary butyl with trans, and then there is benzene ring. So don't panic, even the structure look complicated. Find the right carbon and just connect, then figure out the stereochemistry. Let's move to next question, which is 26.23. Okay, what compound is needed to convert styrene to each product using a Heck reaction? Styrene is this unit. That's styrene. This is styrene, and all of these have trans connection. So this is a trans product. This is trans compound, and Heck reaction generates a trans compound with electron withdrawing group with double bond. Benzene is phenyl group. The electron withdrawing because they want to share the electron through this conjugation. The electron population on this double bond will be a little bit less than normal double bond. But what do we need? What compound is needed? We need this carbon structure with halogen. So vinyl halide or alkyl halide is needed. Here, A, we need this bromide. For B, we need this bromide. There, we need trans bromide. Here, bromide. All with styrene. That's styrene. So styrene with this bromide, compound A. Styrene with this bromide, compound B. Styrene with this bromide, compound C. Will be formed easily. 26.25. Draw the products formed in each reaction. This is cyclopropanes using carbene chemistry. That's how to make CCl2 carbene. The carbene generated from here is CCl2 carbene with a double bond. It's going to make a cyclopropane ring. Again, the carbene is syn addition. This is one species, and there is double bond. Always double bond is sp2 trigonoplanar flat 120 degree. There are H's. So carbene can attack from the top or bottom. That's exactly 50%. You can draw two structures. I'll just leave it as a racemic. B, this is how to make methylene carbene with two good leaving groups, and zinc iodide will be formed. So CH2 carbene is formed. When this one approaches from the top, the methyl is down. Okay, from the top, then cyclopropane ring forms on top. The methyl is down to minimize the steric hindrance. If it's from the bottom, cyclopropane ring forms and methyl is on top. Okay. C, that's how to generate. There are two good leaving groups, Bl. So the strong acid this is not strong as deprotonate proton, and then C minus Br3. There's leaving group Bl minus. So you have CBl2 carbene, and if that carbene approach from the top, this methyl is down. If that approach from the bottom, then cyclopropane ring forms on the bottom and methyl is on top. Here you generate methylene carbene, and that's the double bond. If it approaches from the top, cyclopropane ring on top. If it approaches from the bottom, cyclopropane ring on the bottom. Because of this steric the existence of this methyl group on top, there is a little bit higher chance the carbene approaches from the bottom, but this is very reactive species, so probably that won't be a big factor. So you have two cyclopropanes. Here again, strong base deprotonate and kick out Cl minus the leaving group. You have CCl2 carbene, and that's going to be added on this double bond to make cyclopropane, and this branches, the substituents are trans each other, so I'm gonna draw those, and CL. If carbene approaches from the top, it maintains its trans. Substituents are trans each other. There are H's, and these H's are trans too. This one is cis. So there are H's. H's are cis too. If you have CL, this is the same condition, forms from the top, then H's are down the same side. I'll redraw Cl, H's on the back, and then the rings are front. of course, the opposite is possible. If H is at front, both rings are in the back. So cis, cis, trans, trans. Let's move on to 26.28. 26.28. What starting material is needed to prepare each compound by RCM, ring closing metathesis reaction? These double bonds, ring double bonds, are produced by Grubbs catalyst, and we know there will be two more terminal compounds. So if we have this structure, then by Dosido type, this will be gone with CH2, CH2. There will be two double bonds. This will be two double bonds, which is your product. So that's your starting material. Okay. This one, right there, there, and then we'll have metathesis. Two double bonds will be formed. That will be this. So that the red compound is starting material. Here, CO2CH3. Then this will make CC double bond. That will leave as ethylene gas. Okay. So red, again, the red structures are the starting materials. It's okay to draw generally like CO2CH3 long chain, part of long chain, and maintain this double bond is 120 degree, supposed to be 120 degree, but this drawing easier to understand and always works. 26.30. Draw the structure of the two products when it's treated with Grubbs catalyst. There will be two products. Molecular formula is this. It's like same molecular formula, different structure. This is isomer. I don't know if it's constitutional or stereoisomer. It looks like these carbon will make double bond, ring closing metathesis, and that is our number 1, 2, 3, 4, 5, 6, and then including oxygen 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 atom ring will be formed. The last two carbons leave as ethylene gas. So how to draw the product? You just simply connect, make 16-membered ring with ester in the middle. This is macro, called macrolactone. The ring with ester is called lactone. And number 1 carbon and number 16 carbon will have double bond. So let's start number 1 and 16 will have double bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not 10. Okay, let's do, this is number 1. That's 16. 1, 2, 3, 4, 5, 6. Number 6 has ketone. Number 7 is oxygen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And number 1 carbon and number 16 has double bond. This is one structure which has cis here, and the other one is trans. Cis trans both will form. Let's move to this bond, one right side, and push all of the group one more. Then that's also 60-membered ring with a trans. This is cis. Key is 60-membered ring. Don't need to draw this as exact same ring, but make 16 membered ring, and number 1 and number 16 has double bond, and number 6 carbon as ester group as a part of the lactone ring. Let's move to 26.32. This is general reaction, a mixed example. That's how to make carbene CBr2 base deprotonate proton, C minus carbon ion kicks out Bl minus leaving group. You have neutral CBr2 carbene, and there is double bond. So you'll make, Bl cyclopropane ring. Only one carbon is added to here, which is this carbon. B, that's palladium, phosphine ligand, base, triethylamine, it's a weak base, and here is electron withdrawing group with double bond, and that carbon, aryl bromide, this carbon will be connected to here to make trans product. So benzene ring will be added, and the bromine to this acid is meta, so you have meta position, there's acid. That's this carbon. C, so this is Heck reaction. The first one is carbene. C, that's palladium, double bond, ligand, a lot of things. Base, this is Heck reaction. So now this carbon will make trans product from there. I'll draw styrene first and trans, and there's a benzene ring. This carbon and this amide is ortho position, so NHCOCH3 is in ortho position, and it's trans. So this is another Heck reaction. D is palladium, boron, this is Suzuki coupling, carbon next to halogen, carbon next to boron. This will make bond. OCH3. This carbon will make bond to this carbon. This carbon is meta to this methyl group. This toluene, this is meta-boro, meta position. So you have CH3 on the meta position. Right. Next is another example of palladium with boron, boronic acid. That's gonna be connected here with here. It remains as trans, and here remains cis. This is the product. And let's move to F. F is Grubbs catalyst. That carbon and this carbon will make double bond. This carbon will make double bonds and leave. So that's 1, 2, 3, 4, 5, 6, 7-membered ring will be formed. I'm going to draw the structure again. 1, this is 2, 1, and 1, the 7-membered ring. 3, 4, 5, 6, 7. 1 and 7 will have double bond. Number 4, there's oxygen. So this is the structure. Link closing metathesis. Next one is carbon chemistry. 2 good leaving groups with zinc iodide will leave, and CH2 methylene carbon is generated. Here you'll have the structure. H, that's organocuprate. The product in A is product in A. Where's A? This is the A. Dibromo compound with organocuprate CH3. So this CH3 will be added to here, and there are 2 bromo groups. So CH3 will switch to this 1 bromine, and the next one, this is probably, it's better to have 2 equivalent or excess. Then we'll have this fused ring system. I, lithium will make organolithium, and copper iodide will make cuprate. 1, 2, 3, 4 butyl group is on this copper, and that vinyl bromide will make coupling. Trans remains 1, 2, 3, 4. So butyl group is on. That's organocuprate. The last one, H, E here will be added. That's gonna be new boron product, the boron reagent. The palladium with boron is Suzuki, and that carbon will be connected to this carbon. So this carbon and this carbon, it's trans. One, 2. Okay, 2 H's are here. So that's your product. Let's move to the last question, which is 26.47. Draw the product. So let's draw the product, and we don't have time enough to digest and apply this retrosynthetic analysis, but we'll try with less than 5 carbons. Okay, first of all, the product of ring closing metathesis will be double bond over here, and this will leave. This will make ring. So the product is benzene ring and this double bond over there. That's the product. For B, the product is this will make double bond, this will make double bond, this will leave, and 1, 2, 3, 4, 5, 6, 7 membered ring will be formed. I'm gonna draw 1, 2, 2, 3, 4, 5, 6, 7. So 3, 2, 1, 4, 5, 6, 7. 1 and 7 will have double bond by metathesis. Number 4 has benzyl. So this is your product. Okay. The product is not difficult to draw. Then it asks, how can we synthesize the starting material? How can we synthesize the starting material? Okay. How can we synthesize benzene? We'll use benzene, and there's oxygen with allylic position, allyl group there, and another allyl over here. How can we make that? First of all, we can start from the benzene, and that allylic bromide with alcohol can make that. So that's another. And this is maybe the third part. I can break down to 3. So first is starting from benzene, and there's Friedel-Crafts alkylation. Then you have Friedel-Crafts acylation. You make AlCl4 minus super leaving group with ketone 1, 2, 3. That. And we want to have alcohol. So our reduction, what kind of reduction is this? I will use sodium borohydride. Then secondary alcohol will be reduced to, secondary ketone will be reduced to secondary alcohol. Then the one base, sodium methoxide or any base, OK base, will deprotonate this proton, will make O minus, and there is allyl bromide. That O minus attack here, kick out. So O minus attack here, kick out. Followed by base. Then you have product. The second one is a little bit longer, but what I see here is this is an acetal form with the same branches. So here is O allylic, O allylic. So we'll use allylic alcohol. Okay, we'll use allylic alcohol to carbonyl compound here. Then this can attack. This can attack one time. Two time. Then you have what do you call this? The protection of carbonium. Yeah. So I'm gonna make this benzyl aldehyde. How can you make this benzyl aldehyde? I'll redraw. Benzyl aldehyde, 2 carbon, can be from benzyl, not benzyl alcohol, some alcohol with 2 carbon, OH. How can we do this? This is PCC, mild oxidizing reagent. And how can we make this? 2 carbon with oxygen. What I see is epoxide. And if benzene can attack here and open with proton source, you can make this alcohol. How can you have this benzene attacks and open the epoxide ring? It's easy to buy. Phenyl, magnesium, bromide, and that epoxide is easy to buy. If you want to make this, there will be other ways to make from bromobenzene with magnesium. And how can you make bromobenzene? How can you make bromobenzene? Then you have benzene with bromination condition, Lewis acid. How can we make that? That with oxygen source, which is MCPBA, metachloroprobenzoic acid, that epoxidation. Okay. Then how can we make this double bond? By elimination under acidic condition. Then that's our beta elimination. So, but I expect this green yarn with epoxide attack, open the ring, you can make this. PCC will deliver aldehyde. Okay, and then you have alcohol, allylic alcohol that attacks. I have O minus with O H, and then under, yeah, you'll have this O minus. Under acidic condition, this acidic condition with this alcohol will generate good leaving group OH. This O minus attack, kick out the leaving group, delivers acetal. Okay, this is the end of chapter 26. You guys did a great job, and I'll see you in the class. Hope all the best for you this last week. Thank you.